Hello students, welcome to the lecture on expected value of perfect information learning. And after the lecture we will be able to learn the following objectives: explain incremental analysis, understand the correlation and regression, explain the derivatives, define the chain rule, describe the second order derivatives, discuss the theory of extreme. Let's start with a brief introduction to the expected value of perfect information learning. Expected value of perfect information (EVPI) is the difference between the expected value with additional perfect information and the expected value with current information. The expected value of perfect information is the maximum amount a decision maker should pay for additional information that gives a perfect signal as to the state of nature. Information about consumer preferences might come from market research, additional information could come from product testing, or legal experts might be called on. The expected gain is the expected value of perfect information or EVPI. Let's now learn about incremental analysis, make or buy. We make a component ourselves or farm out the work to someone else. Qualitative considerations may or may not override quantitative issues. Sell or process further issues often arises in industries which refine raw materials. Special order. It typically involves a special request from customers who want a reduced price or some sort of special work. The changes in production and or technology. Modifications in production processes or acquisition of new machinery typically entail adjustments in costs. Why use incremental analysis? Managers typically make decisions by selecting between at least two alternatives. Because there is often a lot of data and information available, a manager's time is used more effectively if he or she examines only the amounts that differ between the decisions, deciding what is relevant and what is not relevant. The easiest way to think about cost when deciding are they relevant or not is to set up two columns and label each with a respective decision alternative. We will now study correlation. Correlation is a measure of association between two variables. The variables are not designated as dependent or independent. The two most popular correlation coefficients are Spearman's correlation coefficient ρ and Pearson's product moment correlation coefficient. The value of a correlation coefficient can vary from -1 to +1. A -1 indicates a perfect negative correlation, while a +1 indicates a perfect positive correlation. The standard error of a correlation coefficient is used to determine the confidence intervals around a true correlation of 0. Let's learn about positive and negative correlation. Some examples of a series of positive correlation are heights and weights, household income and expenditure, price and supply of commodities, amount of rainfall and yield of crops. Some examples of a series of negative correlation are the volume and pressure of perfect gas, current and resistance, keeping the voltage constant, R equals to V by I, price and demand of goods.
Alright, in this lesson we are going to begin looking at scatter plots. And just so you know, scatter plots are where two sets of data are plotted as an ordered pair as an XY coordinate to determine the type of relationship between the two sets of data. So you can see here that in this far left example here, I compared students, how many students per computer were used in each year. Okay, so year was my X coordinate and students per computer was my Y coordinate. Here I looked at the average annual rainfall versus the average annual temperature, and I'm trying to determine is the temperature higher in years where it rains more or less? That's what I want to know. And so I plot them as an ordered pair, and here I'm looking at years and income. Okay, so what's happening to the income as the years change? Alright, then there's this fancy word called correlation. And correlation describes the type of relationship between two sets of data. So in the far left example, you're talking about positive correlation. Basically, if you think about that as a line, positive correlation is a line that would have a positive slope. Okay, and in this far left example right here, positive correlation does, if you kind of think about a line going through those dots, that line does have a positive slope. It's also important to know this. As you move along that line, and remember we always move from left to right, so as you move along that line, your x values are getting bigger because I'm moving to the right, and my y values are also getting bigger because I am moving up. Okay, so that's why I say as x, this is an up arrow for increases, as x increases, y also increases. Okay, here when you move from right to left, if I look at negative correlation, as I move from left to right, I think I said right to left, but left to right, you always move left to right, just like you read. When you move left to right, right here, you're moving to the right, so your x values are getting bigger, but you're moving down, so your y values are getting smaller. So as x increases or gets bigger, your y value decreases or gets smaller. And then over here, when there's really no pattern to your dots whatsoever, then there is no correlation. Okay? So positive correlation would mean you have a line with positive slope. Negative correlation would mean you can kind of fit a line to it that has negative slope. And no correlation means you can't really fit a line to it. Okay? So we are going to go back and look at these three examples here and determine whether they have positive correlation, negative correlation, or no correlation. Okay, so this one, if I were to fit, it does fit somewhat of a linear pattern. It's not perfect, but it is fairly linear, and I would probably draw the line something like that. And so because this line has a negative slope, it has negative correlation. In the middle example here, I really can't fit a line to that. I don't know whether I should fit a line that goes this direction, that direction, this direction, that I really don't know. I can't fit a line to it well at all. So this one would have no correlation. And then the far right one, if I were to fit a line to it, I would probably fit a line something like that. I know it's not real straight, but that line does have positive slope, and so it does have positive correlation. Okay. And that's it.
We will now discuss about the design of job description. Regression analysis in general sense means the estimation or the prediction of the unknown value of one variable from the known value of the other variable. It is specially used in business and economics to study the relationships between two or more variables that are related casually and for the estimation of demand and supply graphs, cost functions, production and consumption functions, and so on. Regression analysis is a mathematical measure of the average relationship between two or more variables in terms of the original units of the data. Let's now understand performance appraisal. Suppose we have a sample of size n and it has two sets of measures denoted by x and y. We can predict the values of y given the values of x by using the equation called the regression equation, which is on the screen. Where the coefficient a and b are given by on the screen, let's study derivatives. The concept of derivative is at the core of calculus and modern mathematics. The definition of the derivative can be approached in two different ways. One is geometrical as a slope of a curve, and the other one is physical as a rate of change. Physical concept of derivative. The main idea is the concept of velocity and speed. Indeed, assume you are traveling from point A to point B. What is the average velocity during the trip? It is given by average velocity equals to distance from A to B over the time to get from A to B. Geographical concept of derivative. Consider a function y equals to fx and its graph. Recall that the graph of a function is a set of points, that is x and fx, for x is from the domain of the function f. We may draw the graph in a plane with a horizontal axis, usually called the x-axis, and a vertical axis, usually called the y-axis. Let's now discuss about chain rule. First, we will multiply the product out and then take the derivative. Then we will apply the chain rule and see if the results match as shown on the screen. So, rules check out, at least for this example. It turns out that this rule holds for all composite functions and is invaluable for taking derivatives. The chain rule, a more formal approach. The chain rule can be thought of as taking the derivative of the outer function applied to the inner function and multiplying it times the derivative of the inner function. Now let us talk about using the chain rule for one variable. Partial derivatives of composite functions of the forms z equals to f gx y can be found directly with the chain rule for one variable.
Okay, let's do some chain rule for partial derivatives. Okay, I've got this function of two variables, so it's kind of like a surface, and I actually got a good example of this surface. Okay, you know, this is pretty much the same thing. It's, say this is the x-axis. You know, we got sort of an upside down parabola. Excuse me, and this is y-axis. You know, we spin it on its side. You know, and as long as its height is 4, I mean, this isn't a stretch at all to kind of visualize this. So if I wanted to describe to you how it's changing, I would use partial derivatives. I give you partial of x and partial y, which are really simple. You know, negative 2x, negative 2y are the partials for this. But with the chain rule, I can actually just kind of give you the derivative of the whole thing. Okay, you know, but if I did that, I would have to somehow link w, x, and y together. And that wouldn't be too hard to do either, you know, because, you know, x is equal to cosine theta, y is equal to sine theta. I mean, we're not going to do that now, but let's just kind of just think to ourselves that, you know, it's kind of like w is now a function of x, which is a function of t and y, okay, like that, all right? So with that sort of approach, okay, we can give you kind of the derivative of the whole thing. So what I'd be looking for would be dw dt. Okay, so let's just go ahead and do that. So what am I going to do right here when I get to the 4? That's just a constant, so its derivative is 0. I get to my x term, and x is actually a dependent variable on t now. Okay, so I'm going to go ahead and take its derivative. Okay, but I'm also going to write dx dt next to it because t is the independent variable. Okay, and really, this is almost exactly like implicit differentiation that you did in Calc 1. Okay, it's really not much different at all. So now I get to my y term, and the same thing. Y is a dependent variable of t, so I'm going to go ahead and take the derivative. But since I don't know what the derivative of y is with respect to t, I'm just going to write it, you know, generically. Right there, just like that, okay? So, you know, but basically, what did we do? We basically took the partial with respect to x, and I guess I almost put an f there, but I guess it's a w, times the regular derivative with respect to t, and I guess the, you know, subtraction is really just addition of negative numbers, and I'm just trying to write the general kind of plain old vanilla formula here. dt, like that. Okay, so that's basically all it is, you know. I mean, it's pretty much the exact same thing. I think, like, it just kind of gets confusing because, you know, in your book they draw all these like little diamond diagrams and chains, and they throw all these weird proofs like right away. I believe in seeing proofs later on after you thoroughly understand this. So I think books tend to confuse people over something that's really pretty simple. Okay, so at the end of the day, though, after you take the you know, the chain rule derivative of this thing, there is one catch though, and that is that, you know, you're probably going to want your answer in terms of t. Okay, since we're taking it, you know, since we kind of parametrically defined everything. And like I said, that wouldn't be hard to do. You know, x is, you know, we know the identities. We should know the identities by heart now. So that's just basically an intro to the chain rule, and we'll definitely do some examples. And you can also do this with 3 variables and all that stuff. So hope this just kind of gives you some insight. I mean, it's really not that tough, but I think books kind of make it out to be kind of a nasty creature sometimes. At least the ones I do. So I will see you in the next videos when we do examples.
Now we will have a look into general chain rule with 2 variables. The following general chain rule is needed to find derivatives of composite functions in the form z equals to fxt yt or z equals to fx sty st in cases where the outer function f has only a letter name as shown on the screen. We assume in this theorem and its applications which are shown on the screen.
It's just going to be a short note about higher order derivatives. So we've seen so far first derivatives, so that is partial derivatives with respect to x and y of a function of two variables. But you could just as well define some higher order derivatives, so second order derivative, for example, in these cases. So if you remember that fx here, the partial derivative with respect to x of the function f, is a function of xy itself, or you could take it as a function of xy itself. Therefore, you could take the derivative with respect to x of this function, and then this will give you what we call the second derivative with respect to x, or the second order partial derivative with respect to x, and then you could write it this way or this way here. Alright, so remember this d is curved here because I have a partial derivative. Now I could do the same thing, but you see my partial derivative with respect to x is a function of x and y, so I could take the derivative with respect to y of this function to get what we denote f subscript xy, and this means the partial derivative with respect to y of the partial derivative with respect to x. Okay, and then this is the similar notation here. Notice though that the order xy here is flipped in these two notations, so just be careful. Okay, this is saying that here you take the partial derivative with respect to y of the partial derivative with respect to x, but it's just the opposite in this notation. So be careful with that. And then the same thing, we define fyx and fyy, and these, you see we have four different types of second order derivatives here. Alright, and then similarly, well, we have third order derivatives, and then we could decide to take, for example, two derivatives with respect to y and with respect to x, and one with respect to y, or three with respect to y, etc. Okay, so you just can keep going here. Alright, so this is just to point out here that you have more than two second order partials. You actually have four. So now you could pause this video, copy this down if you want.
Let's learn the theory of extreme. An important application of critical points is in determining possible maximum and minimum values of a function on certain intervals. The extreme value theorem guarantees both a maximum and a minimum value for a function under certain conditions. It states the following: if a function fx is continuous on a closed interval ab, then fx has both a maximum and a minimum value on a and b. The procedure for applying the extreme value theorem is to first establish that the function is continuous and the closed interval. Now, in the end, let us summarize what we have learned in this lecture. Expected value of perfect information, EVPI, is the difference between the expected value with additional perfect information and the expected value with current information. Incremental analysis is a technique that is used to assist decision making by assessing the impact of small or marginal changes. Correlation is a measure of association between two variables. The variables are not designated as dependent or independent. The difference quotient to make a new function which determined was derivative of the original function. If two variables are significantly correlated and if there is some theoretical basis for doing so, it is possible to predict value of one variable from the other. This observation leads to a very important concept known as regression analysis.